Year 12 classes. I'm just going through the Year 12 mock. I've already gone through questions, or the first few questions in class with one of my classes, so this is just me saving a bit of time and going through the rest of it on here so you can watch it for homework. Right, so the first calculation you got was this question. It was a back titration. Some runners take tablets to help muscle recovery after long races. So we've got some tablets and they contain magnesium oxide. So we've got these tablets with magnesium oxide in MgO. A student wants to find out the percentage by mass of magnesium oxide in the tablets. Magnesium oxide reacts with hydrochloric acid to form magnesium chloride. Okay. In this experiment, the student adds excess hydrochloric acid to some tablets. So they've got some hydrochloric acid in here and they're going to put some tablets inside here. The tablets are going to go in there. The student will then do a titration using sodium hydroxide to find out how much of the excess acid is left. Alright, so this is a typical back titration question. So this acid is in excess. So what they're going to do is they're going to put some magnesium oxide into the hydrochloric acid. The hydrochloric acid will then react away like this. Magnesium oxide will react with hydrochloric acid and some of the hydrochloric acid will be used up. We're then going to do a titration to find out how much hydrochloric acid is left at the end. So let's read the rest of the question and see where it leads us. The student follows this method. They put a beaker on a balance and recorded the mass. They added 6 tablets to the beaker. 1, 2, 3, 4, 5, 6. They recorded the mass, so they know the mass of the tablets. They added some acid to the beaker and stir until it all reacts. So that's magnesium oxide reacting with hydrochloric acid. They've then made the mixture up to 250 centimetres cubed in a volumetric flask, 250. They've then put some of that in a conical flask, here. They've added some indicator, and they've done some sodium hydroxide from a burette until the indicator changes colour. They've repeated the experiments, blah, blah, blah. Okay, the tablets weigh 2.14 grams and the average titer is 2.38. We'll come to all of this in a second. Each reading from the balance has an uncertainty of 0.005 grams. Alright, calculate the percentage uncertainty in using the balance. So with percentage uncertainty, there's the uncertainty per reading. We've got to work out how many readings they did. They recorded the mass and they recorded the mass, so there were 2 readings. So the uncertainty is 0.005 times 2 divided by the reading that you took, 2.14 grams. You times that by 100, the percentage uncertainty is 0.467. I've just read that off the mark scheme, I couldn't be bothered calculating it. Alright, so not many people got this right. One of the issues is a lot of people rounded this, but it says on the mark scheme you need 2 significant figures or more. Don't round unless you are told to round. Alright, so all of these numbers are to 3 sig figs, 4 sig figs, so keep it to that sort of detail, please. Don't round it. So if you wrote 0.5 on there, you didn't get the mark, which is annoying, isn't it, for you? Right, next. Calculate the amount in moles of hydrochloric acid that was added to the tablets in step 3. Now, it's a bit frustrating for you in the exam that you had to turn over the paper. Amount of hydrochloric acid in step 3. 25 centimetres cubed of 2 moles per decimetre cubed hydrochloric acid. So, moles equals CV over 1,000. So 25 times 2 divided by 1,000 equals 0.05, but it says appropriate precision. So what you've got to do here is the numbers with 25.0, so that's 3 sig figs, and this is 3 sig figs. So your answer needs to be 0.0500. Now I know some of you are looking there and I've marked that correct. If it wasn't to the appropriate sig figs, I've only just realised now and you've got away with it. 0.0500, because the numbers in here were to 3 sig figs. Alright, next bit. Use your answer to question 7.2 and the information given to calculate the percentage by mass of magnesium oxide in the tablets. Alright, let me remind myself then. So we had, here's some tablets. There's 2.14 grams of tablets and they were put into some hydrochloric acid, HCl, of which we have 0.05 moles. That's from that number. Okay, so we've got this many moles of HCl. What then happened after these were stirred? They reacted, and I took the excess acid and I put it in a volumetric flask of 250 centimetres cubed. I then, from that volumetric flask, did a titration with 25 centimetres cubed. And in here was some NaOH. Just going to check the concentration of that. 0.09 and 20.38. So the concentration was 0.09 and the volume was 20.38 centimetres cubed. There's NaOH. This is HCl. This is HCl. And these are made of, what are they called? Magnesium oxide, but not pure. I've got to crack on now and work out the percentage uncertainty. So, first little job, I'm going to start here. I'm going to work out moles of NaOH, and I'm going to write it, moles of NaOH. I saw too many where it wasn't obvious what you were doing. Moles of NaOH is going to be 0.09 times 20.38 divided by 1,000 equals 0.00183342 moles. All right, there's my first mark. I've done that. If I know moles of NaOH from here, these react in a 1-to-1 ratio, sodium hydroxide and hydrochloric acid. So I'm going to write, therefore, I've got 0.00183342 moles of HCl in 25 centimetres cubed. So I'm here. I know how many moles of HCl are in here. From 25 to 250 to go this way, I'm going to times that by 10. So if I know moles in 25, if I times it by 10, I'm going to get moles in 250. So taking this number and timesing by 10 will give me 0.018342 moles. Okay, if you got this number of moles wrong, you can still get the mark for doing times by 10. So I now know how many moles of HCl were in here after I added the tablets. So now I know, look where I'm writing, this is how many moles I had before I added the tablets of HCl, and this is how many moles after I added the tablets. So your next step is to do 0.05, that one, minus 0.018342. And I saw this on a lot of people's work, and then you just couldn't get the right answer, like you couldn't do minus on the calculator, or you made an error with this. The answer for this is 0.031658 moles, and a lot of you need to work out what that is you've just calculated. That's the moles of HCl before, that's the moles of HCl after. So this is the moles of HCl which reacted with MgO. So you get a mark for this. Now I'm going to look at my equation. When MgO reacted with HCl, for every 2 moles of HCl, there was 1 mole of MgO. So this is the moles of HCl. If I divide that number by 2, I will get 0.015829 moles of MgO. And this is the moles of MgO in all of those tablets that I put in. Next thing I can do then, if I can go moles of MgO, if I times the moles by the MR, I can work out the mass of MgO in grams. Now the MR of MgO, magnesium is 24.3, oxygen is 16, so the MR is 40.3. I'm going to times that number here, moles, by 40.3. That will give me 0.6379 grams of MgO in all of those 6 tablets. Final step then, 0.6379 grams out of the 2.14 grams you put in, times that by 100, that will give you 29.8% purity, percentage by mass. Alright, try it again, do it again until you get it right. A lot of people got the wrong number, but they only missed a couple of steps out that was slightly wrong, so pretty decent. Define a standard enthalpy of formation. Right, a few people missed this out. The enthalpy change when 1 mole of. Now at the time I said TECWOMO. The enthalpy change when 1 mole of. Now it's enthalpy of formation. A substance is formed from its constituent elements. The enthalpy change when 1 mole of a substance is formed from its constituent elements, and then with everything or all substances in their standard states under standard conditions. So that's the second part, standard states and standard conditions. 1 mark for all of that. The enthalpy change when 1 mole of a substance is formed from its constituent elements. Anything of this missed, no marks. All right. Some people just said when 1 mole is formed. Some people said constituent atoms. Wrong. Learn it properly. Learn. A lot of people fell a bit flat on that, not quite learning it properly. Okay. Silver nitrate 5 is for, so we're going to work out what these things are later on in our next topic. Silver nitrate 5 is formed when silver nitrate 3 undergoes thermal decomposition. All right, so we're told that 2AgNO2, AgNO3, I'm just missing out the state symbols, hopefully that won't come and bite me. We've got this 56.2, I've got that number from there. The standard enthalpy of formation of AgNO3 solid is minus 123. There's AgNO3. The formation of this is minus 123. The standard enthalpy of formation of NO, this one, is plus 90.4. Determine the standard formation of enthalpy of formation of this, and there are 2 of them, so that's 2x. So I know that plus, so if we going from here to here is plus 56.2 is the same as going down here and with these, so minus 2x, minus 123 plus 90.4. I'm going to rearrange this. Let's just see if I can do it quickly. I'm going to add 123 onto each side. 123 plus 56.2. Oh, I wrote it wrong. 123 plus 56.2. 179.2 equals minus 2x plus 90.4. All right, so I'm going to take the 90 off each side. Put minus 90.4. 88.8. 88.8 equals minus 2x. So just swap them around. Minus 88.8 equals 2x. X equals minus 44.4. Just check I've got that right. Minus 44.4, yes. All right, you can get a mark if you just divided something by 2 at the end, which is quite lucky. A lot of people miss the minus off. Suggest why the enthalpy change for the thermal decomposition of solid silver nitrate is difficult to determine. Right, there's a couple of things here. When it says suggest, it means you don't know it. You just got to have a good go. Right, why is the enthalpy change for the thermal decomposition of solid silver nitrate difficult to determine? Thermal decomposition is when you heat something up and it breaks down. So my question to you is, how are you going to measure the temperature change in a reaction if you are at the same time heating it up? So that was one answer. It's very difficult to measure the temperature change or to work out delta T if you are heating it up. So that could have got you the mark. Another thing you could have said, it's quite difficult to measure a temperature change of a solid. Where are you going to put the thermometer? All right. Another possible, which some people guessed, is side reactions might happen. Okay, that was just quite a good random guess. You're heating this up. If it breaks down into all of these things, you could get side reactions. So some people even suggested maybe the silver will oxidize. That was quite cool. Right, next then. That was a hard question. This was not a hard question, but was really, really badly answered. So they've got this reaction here. They're taking some silver nitrate. It says they're going to go measuring cylinder. They put the silver nitrate into a glass beaker. So there's some silver nitrate solution, AgNO3. They're going to weigh 2 grams of sodium chloride, this stuff. They're going to chuck that in there. They've used a weighing boat. Reweigh the weighing boat. They've added a lid to the beaker. They've stirred it with a plastic stirring rod, and they've recorded the maximum temperature reached. This experiment sucks. All right, what they should have done is they should have used a polystyrene cup rather than a glass beaker. So what it says, identify 3 aspects of the method which cause inaccurate results. Inaccuracy 1, using a glass beaker. Improvement 1, polystyrene cup. It doesn't say you have to say why. You don't have to say because it's a better insulator or anything. You just have to say glass beaker was bad, polystyrene cup is better. Inaccuracy 2, a measuring cylinder. Now, they've used a measuring cylinder. They could have used a burette or a volumetric pipette. If you just wrote pipette, you could have been referring to one of those little squeezy pipettes, which is wrong. So you have to say specifically a volumetric or a graduated pipette. All right, you didn't have to say why, you didn't have to say because it's more precise. Some people said they should have changed the way they were weighing it, but that wasn't an acceptable answer because the sodium chloride was in excess, so it didn't matter if it was a little bit weighed incorrectly. By the way, I think actually they've weighed it in a pretty nice way anyway. They've reweighed the weighing boat. There's a lot of ways in that sentence. All right, nothing wrong with the lid to the beaker. Nothing wrong with a plastic stirring rod. People having a go at plastic. You need a glass rod. Plastic also doesn't react. That was fine as well. This is the issue. Just recording the maximum temperature reached. Well, one thing they forgot to do is they forgot to record the initial temperature. They forgot to record the initial temperature. Improvement, they should have recorded the initial temperature to work out a temperature change. All right. Another thing is, just instead of recording the maximum temperature reached, they should have taken the temperature of the solution for 3 minutes. On the 4th minute, added the sodium chloride. On the 5th minute, 6th minute, 7th minute, 8th minute, they should have taken the temperature readings. They should extrapolate on a graph of time against temperature to work out delta T. You had to write all of that and you only got that much space. So it says here on the mark scheme, I'm going to read it, they didn't take into account the heat loss or their method to determine maximum temperature was not effective. They should have measured the temperature at suitable time intervals, plotted a graph and extrapolated to determine the maximum change. All right. So, another inaccuracy which nobody spotted. If you're trying to get a big temperature change, they could have used more concentrated silver nitrate. They've actually used very, very dilute silver nitrate. They could have used more concentrated silver nitrate. Nobody spotted that. What else? That'll do. Right. Empirical formula. This was done generally well. Some people messed it up. Hydrocarbon made of carbon and hydrogen only. Carbon and hydrogen. I've got 0.5 grams of it. I know it's 0.45 grams of this. It must be 0.05 grams of this. If I divide this by 1, and if I divide this by 12, I get this answer, 0.0375, 0.05. People didn't know what to do with this then. Divide both by the smallest number, 0.0375, divided by 0.0375. This gives you a ratio of 1 to like 3. What's that give you? Lost track. 0.05 divided by 0.0375. 1.333333. This is 1 1/3. So if I times both of these numbers by 3, I get a 3 to 4 ratio. So the empirical formula is C3H4. Easy marks, easy money, 3 marks. Some of you messed that up, didn't you? Right, next. This question is about CFCl3. CFCl3 is the propellant used to be the propellant used in most aerosol cans. Use IUPAC rules to name CFCl3. This is, so we've got a fluoro and a trichloro, but alphabetically trichloro, fluoro with a U in it, methane. No other names accepted. Give an equation for the 2 propagation steps in the conversion of this into this. Propagation steps then, that, plus. Give an equation for each of the 2 propagation steps in the conversion of this into this. So in propagation, we've got Cl dots, Cl2, HCl. So these are things I've told you to learn before. This is always the case. Then what you do is you put this chemical here, CHFCl2. You put your product down here, CFCl3. So all you've now got to work out is this and this. In the first step, the chlorine radical always pinches off an H off this. So all I've got to write is CFCl2 and put a dot on it. And then you bring this chemical down, CFCl2 with a dot on it. Watch that bit of the video back, because that's never going to be hard. 2 marks. This was answered really badly. So what did I do? 2 arrows, 4 pluses. I filled in this space, this space, this space, this space, as they're always filled in. I put the reactant and the product in here. Reactant, product. All I've got to do is work out that. In the presence of UV radiation, CFCl3 breaks down in the upper atmosphere to form chlorine-free radicals. Right, write the equation for this. Okay, CFCl3 breaks down, so it doesn't react with anything, to form chlorine-free radicals. Chlorine-free radicals, that's a chlorine-free radical, so I'm going to show one of them here. So if a Cl, chlorine-free radical, drops off, that must leave CFCl2, and that will also be a radical. So that's like an initiation step. In your notes, look at CFC's initiation. This is in the presence of UV. You didn't have to write UV there. Right, okay, chlorine-free radicals catalyse the decomposition of ozone. Oh my goodness, this is absolutely bog standard. Some of you just didn't learn this. That was really pretty bad. Right then, so, ozone, O3 becomes O2. O3 becomes 2O2. No, I'm not looking at my notes here. This is just what happens. Chlorine-free radicals. Chlorine radicals are regenerated. The chlorine plucks an oxygen off the O3 to form ClO dot. There's all my lights going off because I haven't moved for a while. Hopefully you can still see the video. Yeah, and then I put ClO dot. Right, I'm just going to go and turn the light back on. Thank you, miss. I'll stop the Searle coming in and turning my lights back on. Right, so again, that was 2 very, very easy marks. That was just learning. Okay, the production of CFCs. So Jay, state why ozone in the upper atmosphere is important for life on Earth. Right, so you need to say that CFCs absorb UV radiation. That's important, but then why is that important for life on Earth? Because UV radiation is harmful. You could get that. Causes skin cancer. Causes harmful cell mutations. All right, so you have to not just say removes or absorbs UV. You have to say absorbs UV, but you have to say why that's important for life on Earth, because UV is harmful. Right, we're on to this question now, which caused quite a lot of grief. So we've got a compound here, and we're going to talk about EZ isomerism. Firstly, we've got to say what stereoisomers are. This is just a learning fact. Stereoisomers, same structural formula, different arrangements, sorry about my spelling, of atoms in space. Learn. I saw people say same molecular formula, wrong, same structural formula, different arrangements of atoms in space. God, that isn't actually writing that I've done there, is it? Now that gives you point 1A and point 1B. This is stage 1. Could they do that? Yes, I can. How does EZ isomerism occur? Right, well, EZ isomerism occurs when you have a CC double bond. What you have to say, how does EZ isomerism occur? There is a lack of free rotation around a CC double bond. That's what you have to say. All right? That gets you marking point 2A. There is a lack of free rotation around carbon-carbon double bonds in general. Just in generally, how does the EZ isomerism occur? And so if each carbon in the CC double bond has 2 different groups attached, all right, so you need each carbon to have 2 different groups attached. So you can only get EZ isomerism if you've got a double bond with a lack of free rotation around the double bond, and each carbon has 2 different groups attached. For example, A and B, C and D, or I'll go D and E. 2 different groups attached. So you get 2B for doing this. Right. Your next bit you've got to do, explain how the Carr-Ingold-Prelog rules can be used to decide whether J is an E or Z isomer. All right then. So, when using the Carr-Ingold-Prelog group rules, what you do is you look at the groups attached to each carbon and we assign priorities to them. So if I look at the carbon on the right, and I would have to explain this, the right-hand carbon, the right-hand side carbon, the hydrogen has got an atomic number of 1, and the carbon has got an atomic number of 6. That means that the CH2-CH3 group is a higher priority. So CH3-CH2 is higher priority than H+. So I might even write this down here. CH2, so CH3, is a higher priority than H. I think I just said H+ by accident. Okay, so this is the higher priority, high priority. This is low priority. And I would have explained that here because carbon has an atomic number, not a mass number, an atomic number of 6. Hydrogen has an atomic number of 1. On the other side, I've got CH2, CH3, and I've got CH, CH3, CH3. I've got to assign priorities here. So on the left-hand side, I would write this. On the left-hand side carbon, I have 2 groups attached. This group, the CH2CH3, goes from a carbon, 6, and the next atom along is another carbon with a group of 6. This group, with an atomic number of 6, sorry, this is attached to a carbon, which is attached to a carbon, which is attached to another carbon. Any sort of mention that this group is a higher priority than this group will get you that mark. It says in here, has the student indicated in some way that this group that I'm pointing at is higher priority than this group because of the atomic numbers? All right. This carbon here has got a mass of 6, an atomic number of 6. It's joined to another carbon and 2 hydrogens. So it's attached to a carbon and 2 hydrogens. This carbon is attached to a hydrogen and 2 carbons. This has got a higher priority. All right. Then, the 2 high priority groups are opposite each other, which makes this isomer E, because the highest priority groups are opposite sides of the C double bond C. So, a lot of people didn't know that, so you missed out on 2 easy marks, or an easy mark for that. A lot of people didn't know the general statement for how does EZ isomerism occur, lack of free rotation about a carbon-carbon double bond. Each carbon has 2 different groups attached. And then this bit, which was fairly tricky, you just had to say CH2CH3 is higher priority than H. This group is higher priority than this, and it's all to do with atomic numbers, and therefore it's an E isomer. But learn this bit better. Okay, everybody, just learn this bit better. What a stereoisomer is, and why EZ isomerism occurs. All right. How far am I through this? Gosh, quite a long way to go. 28 minutes. This question about the volumes of gases involved in some reactions. Magnesium reacts with hydrochloric acid. All right. So, 0.4 grams of magnesium is added to 20 centimetres cubed of 1.5 moles per decimetre cubed hydrochloric acid. Identify the limiting reagent. All right, I'm going to just do it like this. 0.4 divided by 24.3. That'll give me the number of moles of Mg. This is going to be 20 times 1.5 divided by 1,000. That'll give me the moles of HCl. I'm just reading them off the spec. That's 0.0165. This is 0.03. So which is the limiting reagent? So I cover them up. If I have 0.03 of this, I need 0.015 of this because they're in a 2-to-1 ratio. 0.03, I need 0.015. I've got 0.016. This is in excess. This is limiting. So HCl is the limiting reactant. So you get 1 mark for this, 1 mark for this, and 1 mark for justifying that HCl is the limiting reactant. HCl is the limiting reactant because if you have, because you've got 0.03 moles of it, so if you've got 0.0165 moles of magnesium, you would need 0.0, twice this, 330 moles of HCl, and you've only got 0.03. Let me say that again. It's limiting because if you have 0.0165 moles of magnesium, you would need 0.0330 moles of HCl to react with it, and you've only got 0.03. Okay. What you've then got to do is calculate the volume in meters cubed of hydrogen produced. So we know that the HCl is limiting, and we know that we've got 0.03 moles of it. So now I've got to, here's hydrogen. I've now got to work out how much hydrogen is produced. From the limiting reactant you go from, 2 moles of this makes 1 mole of hydrogen. So I know I'm going to make 0.015 moles of hydrogen. Okay, so I'm going to do PVNRT. PVNRT. R equals 8.31. Temperature is 288. That was a good conversion. Pressure is 101,000. Volume is what we're trying to work out, volume of hydrogen. Moles of hydrogen equals 0.015. That was the common mistake. We're working out the volume of hydrogen produced, which means we have to put in the moles of hydrogen produced. PV equals nRT. V equals nRT divided by P. Plug all the numbers in, you get 3.55 times 10 to the minus 4. Common mistakes, incorrect moles. Using the moles of 0.165 was common as well. Right, look through that. Hopefully you understand a little bit better. Propane undergoes complete combustion. Give an equation for the complete combustion of propane, C3H8. Going to react it with oxygen. You're going to make 3 CO2s because there's 3 of these. You're going to make 4 H2Os because there's 8 hydrogens. Now I've got to balance my oxygens. 6, 7, 8, 9, 10, 5 O2s. Use this equation to calculate the minimum volume of oxygen gas needed for the complete combustion of 50 centimetres cubed. If you've got 50 centimetres cubed of this, you'll need 5 times as much oxygen gas. It's 250. Wow, some people made a meal of that. These are all gases. Gas volumes. 1 of these reacts with 5 of these. 1 decimetre cubed reacts with 5 of these. If you've got 50 of that, you need 250 of that. And so people fill this page. Easiest question on the paper if you spotted it. Right. This question was about nucleophilic substitution. You've got this chemical called iodobutane, C, 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 and it's got an iodine in there. All of these are hydrogens. You're going to put that in a test tube. So you're going to put this iodobutane in a test tube. And then you're going to mark this test tube with a cross below the level of the liquid. Below the level of the liquid, maybe somewhere like that. You're going to put some silver nitrate solution in a separate tube. Place a stopper in both test tubes. Hang on. You've got ethanol and iodobutane in a test tube, this one. This tube is marked with a cross below the level of the liquid. Okay, so somewhere like that. Then you're going to get some silver nitrate in a separate test tube, silver nitrate, and put a stopper in both test tubes, okay? Place both test tubes in a beaker of water, 60 degrees C. After 5 minutes, so once they've reached that temperature, so it's a bit like our disappearing cross experiment, they're going to pour the silver nitrate into the iodobutane and they're going to start a timer. So silver nitrate is going to react with iodobutane. Look through the transparent reaction mixture towards the cross. Stop the time when the cross is no longer visible. So this is going to cloud up and the cross will no longer be visible if you're looking through. Identify the yellow precipitate. Well, we do a bit more on this later, but they've got silver nitrate and iodobutane. You're going to make silver iodide. Now, you did a very similar experiment like with this with Dr. Searle in class or Dr. Patel, depending on what class you're in. So silver iodide is produced. You have to draw the graph on here. You were plotting 1 over time. You ended up with a graph that looked sort of like that, and it had to curve up because it was a curve. So there's the first learning point. If it looks like a curve, you draw a best fit line that is a curve. It goes up like this. All right, 1 mark for the points plotted correctly, 1 mark for a curve. Now then, it then says, you then extrapolate that to 50 on the curve. This will give you a reading of 1 over t, but it wants it reported as time. So if I was on here, my 1 over t equals whatever, 0.062. My time, I've got to do the inverse of that. So you were given a range. What if, you have to actually report it as a seconds, not as a 1 over t. A lot of people reported it as 1 over t. Okay, this is about the actual chemistry going on in that experiment now. The student repeated the investigation using 1-bromobutane instead of 1-iodobutane. So what you have here, let's go with, there's iodobutane, there's 1-bromobutane. The actual chemistry that's happening here, in these solutions, some hydroxide, it's not quite like this, but it's a nucleophilic substitution reaction. That's coming in and it's kicking out the iodide. This is coming in and it's kicking out the bromide. Now, I didn't ask you to say that, but you had to spot the learning point on this is that you should have learned that the trend in rates of reaction of nucleophilic substitutions. You should know that a carbon iodide bond will do the fastest nucleophilic substitution, will react the fastest, and a CBr will be slower. And this is because a CBr bond is stronger than a Ci bond. So how will the rate for 1-bromobutane compare? 1-bromobutane will be slower. Explanation, CBr is stronger bond than Ci. And that's straight out of your notes, and you did an experiment with in your organic chemistry. Right, so how will the graph for 1-bromobutane differ? So the times taken will be larger. So I don't know, instead of 125, it might be 150, this might be 100, this might be 75. So if the times are larger, the 1 over times will be smaller. So you'll end up with a graph that sits below the original graph. Now, of course, that is a hard question, and hardly anybody got it right. So a lot of people got these right, slower because of the bond strength. Generally, though, this question was answered really, really poorly. Make sure you know this and therefore know that that's how they like to test it. You do a little experiment. So when the Ci breaks off, the I minus bonds with Ag plus, and that gave you the yellow precipitate. You would get a cream precipitate with this, by the way. So that was a little bit of tricky practical chemistry, but this was the learning required for this. CCl would be the slowest, CBr a little bit faster, Ci would be the fastest because this bond is the weakest. If you need to chat to me about it, come and see me. Right, this one then, bit of organic chemistry. What you've got is this molecule and this molecule. The difference between this molecule and this molecule is this is a Br and this is a Cn. That is, to me, straightforward nucleophilic substitution, because what's happening here is a Cn minus is coming in, bang, bang, and it's nucleophilic substitution. Name of mech, nuke, sub. Outline of mechanism, well, it was just what I've drawn there. Br, you've got 1 mark for showing a Cn with a minus charge and a curly arrow from the lone pair, has to be from the lone pair to this carbon, and from that bond to the bromine. There are your 2 marks for that, 1 mark for nucleophilic sub. All right. It's just got to be right. Why is water not a suitable solvent? Well, firstly, that chemical might not dissolve in water. Secondly, water, if you notice, water has got lone pairs on it, and that means water can also act as a nucleophile. Instead of Cn minus doing this, your water, your OH2 or your H2O could also do that. That's what they were after there, suggesting why water. So you could say water could act as a nucleophile, or this chemical maybe doesn't dissolve in water. Okay, again, a suggest question, right? Suggest question, you meant to just have a pop at it. Right, give an expression for the equilibrium constant for this reaction. God, it's a 38-minute video so far. I think my memory's going to run out on my phone. CH3, CH2, COOH, square brackets, square brackets, square brackets, square brackets, CO, H2O, C2H4. That was a very easy mark. Calculating KC. All right. Big problem with this is that you forgot to use the volumes. All right. What we've got to do is so KC equals, right, the concentration of this, which is the amount of moles, 0.420, divided by the volume. And the volume is already in decimeters cubed, so you just have to divide it by 1.2. 0.062 divided by 1.2. What's that one? 0.07 0.8 divided by 1.2, 0. What we're doing here? 0.062, yeah, 0.062 divided by 1.2. People forgot to divide by 1.2. This is moles divided by decimeter cubed, moles per decimeter cubed. You plug all of those numbers in, the answer is 2017. There's a range you could have, actually, I don't know why. It says there's a range. The units is you've got one volume divided by one moles per decimeter cubed divided by 3 of them, so they cancel out. So you've got 1 over mole squared decimeters to the minus 6. So it is moles to the minus 2 decimeters to the 6, because you have got 2 on the bottom. If you're in the lessons, you'll know what that means. Oh, sorry, I should have put that there. And the answer is 2017-ish. Right. Predict the effect of increasing the temperature on the yield of propanoic acid. Right. There's the equation. That means it's exothermic in this direction. It means it's endothermic in this direction. The question says, what's the effect of increasing the temperature on the yield? When we increase, it's shifting the endothermic direction in N. Right. So if you increase the temperature, it'll shift that way. So the yield of propanoic acid will decrease. So decrease, explanation. When the temperature is increased, the equilibrium will shift in the endothermic direction to oppose the increase in temperature, therefore making it will shift to the whatever that is, left. So increase, shift in the endothermic direction, it will shift to the left to counteract or oppose the change in temperature or the increase in temperature. Right, 41 minutes in on this video. This is done really well. Minus, few people missed 2062. Minus, few people missed that out. This is one of them. You did Q equals MC delta T. You work out the moles of fuel. The moles of fuel was 0.030. So it tells you that at the top. Didn't have to work that out. And Q equals MC delta T. Mass equals 250 grams. C equals 4.18. Delta T equals the difference between this and this, which is 59.8. I'm leaving that because nearly everybody got it right. If you didn't, you've got to go and do that. That's you. That's you, though. You. That person there. You've got to go and do it. Excellent. Right. The answer was minus 2062. Now, you all know that this experiment sucks because heat loss to the surroundings. What that means is that you know that this number, if there wasn't heat loss to the surroundings, this should be a bigger negative number. It should be something like 22,200, 2,300. All right? You know that if this has been done from an experiment, this number will be too small a negative number. Right. So even though 2062 is closest to this, this can be the only correct answer because you know that your experiment had heat loss to the surroundings. So the actual value should have been a more negative number. So the only fuel it could have been is propan 1-ol. The mark scheme then says, okay, basically that. Right. Any idea that your answer on this page was inaccurate due to heat loss, therefore the only feasible answer will have been a more negative or a more exothermic answer. So the only one it could have been is butan 1-ol. Anything around that sort of idea. Gosh, I'm nearly there. Right, this answer, really easy question, right? But hardly anyone gets it right because you mess it up. You'll have just miscounted the bonds. CH3, CH2, 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 OH. Then you've got 7.5 moles of this. And on this side, you've got 5 CO2s. Carbon dioxide has got double bonds and 6 H2Os. So you've got to go through and count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 CH bonds, 11 times 412. A C single bond O, so a 360. An O single bond H, a 463. 7.5 O2, so that's 7.5 times 496. That's that one. That's bonds broken. On this side, 5 lots of C double bond O, C double bond O, so that's 10 lots of 805. I saw a lot of mistakes there, people using single bonds. And then 12 463s, 12 463s. Everything on this side, by the way, adds up to... All of this adds up to 13606. All of this side... Oh, sorry, and you've got 1, 2, 3, 4. You've got 4 x's on this side. All right. So, and I know this is minus 3388. Right, so I then go minus 3388 is the same as going with everything on this arrow, so with all of that junk in there, and then against 13606. The answer, if you then divide something by 4, so the answer will be 4x equals something, you then have to divide it by 4. The answer was 286 kilojoules per mole. Hardly anybody got that right. Well done if you did. That showed you're a very, 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 very good, careful chemist. This question, I am going to go through in class because it's not that hard, but it's quite hard to explain, and I'm running out of time. Tone's gone. Need a coffee. I'll do that one in a minute. Energy density. Draw Maxwell-Boltzmann distribution curve, 2 different temperatures. Right, there's one temperature. You should really label that as temperature 1 or low temperature. At a higher temperature, the top of this will shift down and to the right, so you go down and to the right. They both need to be fixed at 0, 0. The axis is energy E and number of particles with energy E. All of that will get you most of the marks. By reference to these distribution curve, explain why the rate of decomposition increases at higher temperature. All right, so we go higher temperature, lower temperature. You put an activation on there, activation energy. You say at higher temperature, many more particles have energy greater than or equal to the activation energy, so you get many more frequent successful collisions. That's 6 marks. A well-drawn diagram labelled would have got you 4 out of the 6. So many of you couldn't label that, which is a bit embarrassing for you. You and you. And them there, that person there. Oh no, there's a back page. I thought I'd finished. Right, time of flight. Right, SR atoms, gas with electron impact will become SR plus electrons. Weirdly, this question, I thought it was going to be quite hard. A lot of people scored 5 on this. The answer, I'm just going to give you the answer, 84, because it's got to be a mass number. So any decimal places here loses a mark, because mass numbers should be whole numbers. Typical time of flight. If you can't work it out, you can come and see me. That's me, Dr. Norton. Come and see me in class. 50 minutes, though. Goodbye. And well done, you survived your mock.